All right, off we go. So let's learn how to visualize things. Let's make some pretty pictures of pretty graphs, and this is chapter 7 stuff. So please start reading chapter 7. Shouldn't be too bad. It's very exciting. We actually get to make nice things, and this will really help us with a lot of the questions that we kind of had last time about the different data sets that we showed. Like the Titanic data set was very cool and interesting, but some answers are probably better off answered, some questions are better off answered with pictures. And this will be the chapter where we start learning that. So before we get there, I want to talk about the kinds of things that exist in data sets. Like, what are the adjectives that describe the data? Because some things, some types of data, I think you can imagine, are easily graphable, and some types are not. And let's kind of learn the difference, all right? Because there's different kinds of graphs for different kinds of things as well. So let's talk about types of different things we see in our data sets, and the values, the kinds of things that we see in our data sets. There's a bunch of different names for them. They're called values, they're called attributes, they're called features, like the prices of those ice cream cones. What are the values of the prices? The attributes involved, like the features involved. So a bunch of different words for kind of the same stuff. Here are your main ideas. So there's two main kinds of values that you'll see in data science. You have numerical values and categorical values. Numerical attributes or features, categorical attributes or features. Okay, so numerical ones are ones that are numbers. I think you can imagine, like your prices of your cones, ages of people. But numerical attributes, numerical features are values that you can measure and you can count and you can graph very easily. It's already a number. Okay, it's like heights. That's a number, right? Ages of people, that's a number. The temperature of Fresno and the hottest day, the hottest record on February 2nd, that's a number, right? The prices, the HP of Pokemon at level 50, which is apparently what's in our Pokemon data set. That's all numerical stuff, and it's really easy to make graphs for numerical stuff, right? Super, super simple, because they're already numbers. We know how to plot numbers, okay? You do have to do some extra work if they're not numbers, and the alternative, the other flip side of that coin, is called a categorical feature. So a categorical feature is when you don't have numbers. It's you're listing things with labels. You have characteristics, maybe like adjectives, like the color of this ice cream is pink because it's strawberry, something like that. Okay, so like categorical features are just like characteristics, ways of grouping things. You got names and labels, something that's not immediately a number. So like colors. What's the color of the ice cream? What's the state of residence of all the, I don't know, all the people in a set of people. You got like a bunch of dog breeds for every dog that's in like a vet's database. Shirt sizes, small, medium, large. That's not a number, right? It's just it's a letter, it's a word, it's an idea. Types of Pokemon like electric and fire. You see how you can't really graph those yet? They're not numbers or anything. So those are categorical features. If you want to make a graph out of categorical things, you have to turn those values into numbers somehow. One easy way that I'll show you is going to be like counting the frequency, like how many electric Pokemon relatively are in the data set, how many fire Pokemon are in the data set. Like doing a count can eventually give you a number, can't it? So categorical, not immediately a number, a little bit harder to graph. Any questions about those two ideas? Those are like the two main different things that you see in a data set, and we've seen that everywhere, right? We go back to our ice cream cones, very simply. You got flavor. If I zoom, I don't think I can even zoom in, sorry. Like your flavor was chocolate, strawberry. Those are all categorical things, right? There's no numbers associated with vanilla, with chocolate, with strawberry. Same with color, pink, light brown, dark brown, white. All those colors, again, not numbers yet. But price, that's a number. We made another price with tax column. That's a number. That kind of stuff, okay? So that's where we're going. We want to graph them eventually, though. And here are your main ways of plotting numerical things. We'll talk about that first, because they're already numbers, it's easy. Let me show you how to plot things with the dot plot operation on a table and the dot scatter operation on a table. They're pretty much going to do the same thing, where dot plot makes what's called a line plot, and dot scatter makes what's called a scatter plot. I'll explain the difference with an example. But yeah, let's start there. So I would like I'm in my chapter 7 file. I would like to include some data. I'd like to use the data science library, of course. I'll say from data science, import everything. And then I want to do, I usually am going to want to do column-based stuff. I want to do array-based things. So that's NumPy, remember. I'll say import NumPy as NP for short. That's what people usually call it. And then I'm going to include 3 extra lines today that I'll just copy and paste from now on. It's not something that you need to memorize, but it's going to, these lines are about to control the way that graphs get made in JupyterLab land. Okay, so I'm going to say %sign for a weird reason, matplotlib inline, and then import, it's a new library that makes graphs, it's called matplotlib.pyplot, Python version of it, I guess, as PLT for short. Your textbook imports it as like plots sometimes, but I'll just use PLT. That's what the cool kids use. I'll say plt.style.use, and then the way that I want it to use, like pick the colors of the graphs in order, is from a website that had to do with like political things. It's called 538. It's like supposed to be the number of U.S. representatives or something before they. I think that's still the same number, maybe. I'm really not sure. But what these 3 lines do is, kind of the middle one's important. It imports the ability to plot things. You don't have to memorize this. So you don't really have to worry about this too much, but I want to explain them to you at least once. It's like imports the ability to plot things, and then this %sign is controlling how things get plotted. Because when you run a cell in Python, in JupyterLab land, it's going to do something. We're telling it, when I ask you to make a graph, don't like make an extra file, like for the graph or something, to like export it to a JPEG or something like that. I would like to see that graph immediately. Put it inline in my notebook, in my document. That's what that part means. And then plt.style.use 538 as a string. That just means use the color scheme associated with the 538 website. They came up with something, and like those are the pretty colors. And the first 2 colors are like blue and gold, and I think that's why they chose it, because that matches the colors of Berkeley. So that works out. And so that's what you got to do at pretty much the start of every notebook from now on. These are the things that I give you in that little default notebook as well, and now you know why. This is just giving us the ability to do inline plots. That's what I care about. So yeah, with that, I want to start with showing you how to do a scatter plot. That one makes the most sense. It's the easiest one to start with. It's just a bunch of dots, and let's talk about those dots. So let me make a header for that. And what a scatter plot is, let me explain it first. If I zoom in a little bit, that might help. What a scatter plot is you have stuff on the x-axis and stuff on the y-axis, just like every other graph that you could ever want to make, right? And you get to say to dot scatter which one's on the x, which one's on the y. But for every piece of data that you have, for every row in your table, it's going to graph the x thing and the y thing and kind of like throw a dart at that spot. So it'll draw just a little dot. So like we're going to import like a bunch of actors in movies, and like we'll have how many movies they were in. It's like for each dot is an actor then. Like this is how many movies that they were in, and this is like the average amount of money each movie made. Those are 2 numerical attributes that you could graph with. But every dot is going to be a single individual, a single row from your graph with that particular x value and that particular y value. They may overlap, like some of them are very close. Some of them might be the same. You can't immediately see that. But this is a great way of seeing like what's the spread of your data set. It's drawing little darts and throwing them at x coordinates and y coordinates. One dot is associated with every row of your table. Okay? And so it's dot scatter that gives that to you. Let's go to the documentation. So you got a table, you can say dot scatter. And you give it the x column and the y column, and let's not worry about the third thing. It's like actors got scatter, number of movies, total gross. Like for every actor in your actors table, use the x-axis, put number of movies for that actor on the x-axis, put total gross, which is like how much money the movie made, on the y-axis. And that each dot is an actor. Okay, so that's what a scatter plot means. It's a dot for every row, and let's get that working. So let's import a data set. It's called actors.csv. It's just a bunch of actors and what they've like done when this data set was compiled. So actors, let's make a new table. It looks like this. It's in my data folder. It's called actors.csv. Feel free to get that too if you'd like. play around. And so here is just a bunch of actors, 50 of them, a bunch of famous actors, and how many movies they were in at the time that this data set was made, the average amount of money that movie made, the total gross, like how much money all of the movies that they were in made in total, their number one grossing movie, and how much money that one made. That's what they're saying. That's what all those columns are kind of meaning. And money means in millions of dollars. So money amounts are in millions of dollars. So apparently all the movies that Harrison Ford starred in when they made this data set, it was they all together made almost $5 billion. Amazing. So very famous man. So yeah, that's what that data set means. And let's make a scatter plot for this data set. I'm going to say actors.scatter. And then I give what I want to go on the x-axis and what I want to go on the y-axis, the names of the columns. All right? Which numerical attributes, of course, only. So let's put, for each actor, let's graph them. Let's turn them into a dot, where on the x-axis, we're using number of movies that they were in, and then we'll do like total gross, which is how much money all those movies made. And you'll see this again in your textbook as you read it. But each dot got turned into, or each row of this table got turned into a dot. So Harrison Ford, for example, is on this graph where at 41 movies and almost $5 billion of gross revenue. So 41-ish, 5 billion, that's him right there at the top. Do you see where my mouse is? That is Harrison Ford. He got turned into that circle. Does that kind of make sense? For an x value, for a y value, it was plotted. And you can kind of see the spread. So a lot of actors are kind of down here. They're not in that many movies, and not all those movies made a lot of money. But that's interesting, right? That's interesting how that works. And so you can explore your data set with a scatter plot by turning every row into a certain dot on an XY plot. All right. So that's kind of cool. Let's do another scatter plot of this actor's data set. Let's do on the X the number of movies again. And instead of the total amount of money that each movie made, let's do the average per movie. We have this average per movie for each of those actors. So again, we're using each row, but we're turning it into a dot where the X coordinate is number of movies for that actor, and then the average amount of money that movie made is the Y coordinate. So here's a different graph, and this one's interesting. You can kind of see that there's a bit of a trend, right? There's a weird dot up there, first of all, but most of the actors are doing this. Like, it looks like the more movies you're in, the less that each of those movies makes. Like, as an actor, you have to work harder, work in more movies if they're not making as much money. Maybe that's what that's trying to say. Like, you can interpret it that way. Does that kind of make a little bit of sense? But of course, there's a bunch of different ways to interpret it. But that little dot at the top, that's called, like, you see how it doesn't follow the trend. Like, all the dots are right here, and that one just kind of jumps way up there. There's an actor that's not in a lot of movies, but all of those movies made a whole lot of money on average. That was just a lucky actor, right? That's called an outlier. Maybe you've heard that word before, but it's far away from everything. It's lying out from everything. It's called an outlier. And we can figure out who that actor was. You can say actors.where the number, because it's both, like, this person, whoever they were in less than 10 movies, right? Where the number of movies, give me all the actors where the number of movies values are below 10. There's only going to be one in this data set, and it's Anthony Daniels, apparently. And I didn't know who this was before I read the textbook, but he was in exactly 7 movies when they made this data set, which is kind of helpful to think about. Average per movie, they made a whole lot of money, and this was Star Wars. So this person, Anthony Daniels, was the actor who was, I think, C-3PO in Star Wars, and so he was not in a lot of movies. He was only in the Star Wars movies, but each of those made a whole lot of money. And so he picked the right one to star in. He made a lot of money himself, I'm sure. So yeah, that's how you can kind of inspect your data set. Like, okay, I see that there's something weird going on this graph. I see that somebody's way up there. I didn't notice that before. Who is that? And that's how you can explore things. Does that kind of make sense? Any questions about that process, or what a scatter plot is? Each actor is turned into a dot. This dot way up here apparently was 7. There was number of movies was 7, and then the average per movie was a little over 450, which is why that dot went right there. And every other actor is in every other dot. Okay, some of them might be lined up. Questions about scatter plots. It's turning every row of your table into a graph where you choose what was on the x-axis, you choose what was on the y-axis. So I could have done it in the other order, couldn't I? That's a thing. If you want to see, you see that like that Anthony Daniels is kind of like throwing off this graph. I kind of want to see the normal graph for everybody else that kind of like looks normal and has a little bit of a trend line going on. If you heard that word before. You can graph just these guys. You can exclude Mr. Daniels here by doing the following. You can do a dot where. Like, all right, give me the actors. Here's how we picked him, right? Actors where all the movies are below 10. Do the opposite. Give me all the actors where the number of movies that they started in are above 10. Above 10. And that will give you a table which you can then dot scatter on. Does that make sense? So just like everything else, it gives you a brand new table. You're doing dots to get what you want out of it. You can turn this into a graph next. Like, okay, take that new table that had everybody except for Mr. Daniels because we excluded anybody who starred in less than 10 movies. And then we can do a scatter plot on the same stuff that we're doing, number of movies and then average per movie. And so what we're about to do is zoom in on just this part, skipping out on the outlier. So that's kind of neat. And there it is. And so you see like when the number of movies goes up, the average per movie goes down. Usually that just means that the actors are less famous. They have to take more work. Something like that. That's how you can interpret it perhaps. Okay? But that's what a scatter plot is. You have a dot for every row in your table, and you're graphing them with their numerical attributes. You get to choose which numerical attribute is your x and which numerical feature value is your y. Every person gets turned into a dot. Questions about that before I show you the other kind of graph? Another kind of plot. It's called a line plot. All right, so a line plot looks like this, scrolling. It's pretty much the same, but you're drawing a line between stuff. And so usually you use a line plot. It's just like every point is there. Like you can see the jaggedness. That's an XY point. You get to choose again what's on the X, what's on the Y. But usually now the X-axis has some sort of chronology involved, like time is involved. Usually like it's a year or a date. So that you have an order to it all. And you can see the progression, and it makes sense to try to draw a line between things to like extrapolate what happened in between. For scatter plots, that doesn't make sense. Like you can't draw lines between actors and expect anything to make any sense at all. But you can totally draw lines between time and see like, okay, if it was up here and it moved to there, you can imagine that even if we didn't have data on what happened in between, it had to go from there to there in a sense. And you can kind of see a progression in that way. So a line plot, it's all together so you can see a progression over time usually. So, oops, I didn't want to click that. But it's just dot plot. You give what's on the X, what's on the Y, and it will sort by the thing on the X. Right? It sorts the table in ascending order based on your X column that you choose, and then it graphs them all, and it draws lines between all the stuff. So that sorting process just makes it make sense. Okay, so let's do that. Let's do a line plot of some movie stuff. Let's see. Oops. Line plots. So here, let's do another table. I've got another one about movies again, but with some different data. I've got one called Movies by Year with dashes. Movies-by-year.csv. And let's look at those. So this is another data set about movies, not just actors anymore. So movies by year is table, read table. So my data folder is called movies by year.csv. And here is what you get. There's 36 movies apparently, and here are what the columns are. You got the year that the movie was made, how much money that movie made, again in millions of dollars, and let's see here. Total gross. Excuse me, sorry. You got the year that the year that they're keeping track of things. Excuse me. The number one movie that was made that year, the number of movies total that was made that year, and the total amount of money that all of the movies made together in the box office. That's what that means. Excuse me. I looked at this and was like, oh, I forgot that it's every movie at once. So this is what we see. It's one per year, which makes sense. They only took data per year, but it goes up to 2015 apparently. And so let's plot this with some sort of chronology. We got the year, right? Let's put the year on the X. So movies by year. I want to dot plots to do a line plot to keep it all together with the year on the X, and we'll do maybe the number of movies that was made that year on the Y, because you see how it's like fluctuating. That's interesting. So number of movies on the Y, let's see. And this is what happened. It looks like in the 80s, they didn't make a lot of movies. And then, or in the 70s, they didn't make a lot of movies. But then the 80s happened, and everybody wanted to go to the movies. Like, it jumped up from like under 200 to over 500. That's weird. Something must have happened. I don't fully understand. Maybe times got better, like people had more money to go to the movies or something. And that's kind of fluctuating every few years. And it goes up and up and up. They're always making more movies every year up through like 2015. Sometimes it goes down. There's a huge downtrend right there between 2007 and like 2009 or so. What does that mean? Any thoughts? What happened during that time of history? I don't know if you guys learn about this. I guess it depends on how recent they include things in like your U.S. history or world history classes. But like there was a recession. There was the Great Recession during 2008-ish. Have you heard of that? As a thing that we probably don't remember, but because we weren't affected by it, but it happened, and they made less movies because of it. Less people wanted to go to the movies. Fewer people could afford going to the movies. See the recession? There's probably a couple of them. Like there's a few recessions going on here. Maybe that's what you can see, but this was for sure caused by the recession. Crazy. All right, so there's that. And yeah, anything that has chronology, you can use a line plot for. So like year on the X, year is the only thing in this table that makes sense to put on the x-axis, but the other numerical variables could be on the y. You've also got total gross, like how much money all of the movies made that year made in total. That could be your other numerical attribute. Again, line plots, just like scatter plots, can only have numerical attributes on the x's and the y's. There's no way to graph like the name of the movie or something. That doesn't make any sense. So here is the total gross, and you see that going up as well. All right. It looks like they're just making more and more movies, and those movies are making more and more money because inflation is also a thing. But that's what's happening. You can kind of see over time that more money was made on movies. All right, for one reason or another. Could just be inflation, but also a few more movies were getting made as well. So that's the thing. And yeah, you can try to extract information about this graph. You can kind of see, you can't really see the recession anymore. It looks like more money was made on movies during the recession, but fewer movies in total were made because like it was harder to get a loan to make a movie if you were a director or something like that, because it was there's not a lot of money to go around. But the people who did did have the money to make movies, like there were people wanted to watch them. Something like that is something you could think about is a possible conclusion. Of course, you have to look that up further, but these graphs help you with that, formulating those ideas. Any questions about a line plot, what it's doing? All right, so you need some sort of chronology for line plots. And let's see, what else do I want to do? Yeah, I wanna show you how to like zoom in on things. Let's zoom in on a part of this graph that we care about. Let's say that like I only care about the movies and the data from the year 2000 onwards, like the millennium, all right? The 21st century only. So I can be like this. I can be like movies by year. Give me all the 21st century movies. Where the year value, so movies by year dot where. Give me all the movies where the year column values are above 99, right? Because greater than 99 implies 2000 and onwards. You could also do above or equal to 2000, but I'll just do it dot above. It's quicker. And then you get this table of movies from 2000 onwards, all right? 2000 onwards, and you can graph that too. You can put this into a variable. That can be like a table that you want to do data analysis on, but you have to be careful about the way you name variables. I don't know if I told you this in this class yet, but this is a great place to say it. If I want to say like 21st century movies and put that into a variable, I can't. If I hit Shift Enter, I'm going to get an error message. Unfortunately, you cannot name variables that start with a number because Python thinks that like you're trying to do math right now. So your movie or your variable names in Python, they cannot start with numbers, but you can totally put numbers after you started with at least a letter or an underscore. So that's something to know. All right. So you can't start a variable name with numbers. So sad face. And so we got to turn this into something else like century 21. Put it last, all right? And then once you've got that table, you can be like, all right, I got my 21st century movies in the century 21 table. Then I can do a plot of year and number of movies again. Like we can zoom in on the 2000 and afterwards. So you can kind of zoom in on the recession. And there you kind of see the dip very clearly now, all right? So yeah, that's how that works, and that's what it looks like. You can do the same thing for total gross. That was the other column, right? Total gross of just the 21st century movies from 2000 onwards. How much money were they making? And you can kind of see how that's like, sometimes it goes up and down, but there's no real spike anywhere. It's just like gradually getting more, they're making more and more money as inflation increases, as more people want to watch movies and things like that. Okay, so yeah, I think that's what I wanted to say. And then you can always ask a question of like, what in the world was going on when, let's see, like we were down here in the dip. It was 2010. There weren't a lot of movies being made, but it looks like the gross amount of money for the movies was still pretty high. So like, what was the popular movie in 2010 or something? Be like Century 21, where the year was 2010. So where the year values are equal to, remember we could do that and hit enter, but also equal to is the default, so you could have just said 2010. And it looks like it was Toy Story 3 was the popular movie. Even though there weren't a lot made in 2010, it still made a lot of money because it was popular, apparently. And all the other movies as well made a lot of money. So I think that's what I wanted to say about line plots versus scatter plots. So line plots are when you have chronology on the x-axis, something that it makes sense to want to fill in the gaps. And then a scatter plot is when that doesn't make sense. Like you just have a bunch of different data, like you're throwing darts at your graph, and you're drawing a circle. It's like where the dart hits for each individual in each row of your table. All right, so that's line plots versus scatter plots, and kind of when you want to use them versus when you don't want to use them. Yeah, any questions about those before I ask you to try? All right, so let's see. I would like you to try, please, to read in our Fresno max and min temperatures data set again. So that's the one from last time that we used. It's in this file, my data folder, and it's in max min temperatures, Fresno up to 2025. It's a very long name. You can rename it once you get it, but let me get it in here. I'll call it temps. But I'd like you to get it too, please. So you remember how to do it. You got to go, and you can drag it in. You can click the download button. And here it is for every day that you could ever want to have. It will tell you the highest high, the year that highest high record was set, lowest low, and same for that one, the record date, the record year. I would like you guys to please try to graph the temperatures over time. You can only graph one of each, right? You can do the graph the high temperatures, graph the low temperatures, and I want you to think about. You can read this and try it if you want. You look into it on the data set, but like this is the part of the question that I care about you figuring out and trying. Try to graph the highs and the lows of the temperature of like the records over time for Fresno for that data set. Okay, and I want you to think about which kind of graph you're going to need to use here. You can either use a line plot or a scatter plot, and which is going to be the right one. All right, so think about that. You don't have to submit anything, but I want you to try to play around with that data. And I'll give you everything that I've done today if you want to see how I did the scatter plots and the line plots. Let me go and submit all the code that I wrote for us today to our code from class folder. Just real quick. All right, if you go to our code from class page, now you have everything. So here, let me show you where to get it, and then I'll let you work for a few minutes. So I guess you can go to any lecture, but you can also just go to code from class. You can go to data 8. And then here's what we did today, chapter 7 so far, at least. And then in the data folder, it's the max min temperatures Fresno up to 2025, and the download button's right here. This download the raw file, that little download link right there. Is how you can get it on your own computer. And yeah, I think that's what I wanted to say. So please try to graph, like over time, the highest highs, and then over time, the lowest lows for our Fresno data set. And think about what kind of graph you're going to want to make. Is it going to be a line plot? Is it going to be a scatter plot? That's all we've got so far. And please do attendance too if you forgot to do that. I'll stop that after this. It doesn't really make sense to want to graph highest high and lowest low together on like one's on the X, one's on the Y, I don't think. But I mean, it's worth trying. It's worth trying. I'll give you a couple more minutes to play around with that, and then I'll do it too. And then if you want to try this little hint, you just like run this in a cell by itself, and then you try to graph again, it makes it prettier. And you can turn it off by saying this on the line by itself. All right, that's my timer. Did we figure it out? Any questions about how to do this? What kind of graph did we choose? Was it a line plot or a scatter plot? What seems best for this kind of data? Okay, yeah. I think either one would be fine. Though we do have chronology going on, so I think a line plot's a good choice as well. See that? So let's see here. Something like that. But yeah, because the dates are out of order as well, it is kind of up in the air. It's up to you. So that is totally subjective. Let's do a graph. So I would like to, let's do the highest highs. All right, so let's do, I got my temps table. Let's do a line plot. Let's see what it looks like to try to draw lines between them, because there's like the dates, even though they're not probably from the same year for these records, at least you can kind of see the progression from as the seasons go on over time. So I got date on the X for sure, and then let's do highest high on the Y. Let's do a line plot so it connects them for fun. And then you're going to see this. It's going to be very zoomed out, but you can see a pattern. It kind of does make sense to want to, like, if you did a scatter plot instead, you'd see pretty much the same thing. Whee! But they're not as connected. But you can still see the pattern, right? The pattern is the most important thing. You got the summer right there, right? And then it's like you're just going around that. We're around here right now, so we're getting there. But yeah, that's what that looks like on the x-axis. It's trying to say all these labels like 01/01, 01/02, 01/03, but they're so small. There's so many things that they just all overlap each other, and it just looks like it's a dark black. It's crazy. And so if you want to be able to see these dates and play around with it better, I showed you this very briefly one day. It's called interactive plots. If you say table.interactive plots, that turns on a different way of graphing where you can like zoom in and stuff. And so if I say that just on a line by itself, and then I run this again, what will happen is it looks a bit fancier. All right. Then it's like it's zoomed out, and if you zoom in, you can kind of see different pieces of it, though it is kind of harder to play around with. I want to pan. So where am I? So I'm up here. Like you can zoom in as much as you want, and then you can put your mouse over and you can see exactly what was the X value and the Y value. So that's kind of cute and cool to think about. Let's see, auto scale. But that might be a better way to graph it, and you can kind of see the patterns there. The same thing would happen with the scatter plot. So that's kind of cool to think about, and that makes it pretty. So those kind of go together. Like turn on interactive plots, then do it again, and then if you're done with that, you can say dot static plots to go back to like the normal way of graphing things. But we can do the same for lowest low, right? Plot date versus lowest low, or lowest low versus date, I think is how you say it. And you can kind of see the same trend. Like as it gets to be summertime, the coldest temperature, even the record-setting one, is higher, as you would expect. Okay, and yeah, that's what that looks like, and you can kind of see that there's a trend that is the same. Like around the end of July, that's the hottest days in Fresno. Start of August. All right, cool. That's fun to think about. And yeah, when you're done having it be interactive like this, you can say table.static plots to turn that back off and go back to how it was. Static plots. And now if you do another plot, I'll just do it normally. So yeah, any questions about any of that? You kind of see what those graphs look like. Have any questions about them? You see how you can understand, like, oh, there's summer, there's winter. That's how seasons work in Fresno, apparently. Yeah. You can graph weird stuff, though. You can graph anything with a scatter plot, at least a scatter plot, that's two numerical values. You can choose any two numerical columns, so pretty much everything but date, unless you want to turn date into, like, how many days have we been since the start of January or something. You'd have to do some math. Like, all of these are fair game to go in the X or the Y axis of a scatter plot, for example. So, like, you could do this. You can be like temps.scatter You could be like, on the X, you could have the year that the record was set for highest high. And then on the Y, you could have the temperature that set the record. And this is going to look a little weird, but you can still try to interpret this graph. So, right on the X, you have the year that the highest high was set, and then you have the temperature that highest high had. And the way that you can kind of interpret this, I hope you can see that the graph is a bit more sparse over here. There's not as many dots on the left, but there's more dots on the right. So that's implying, you see how that's implying that the records were being set more often in recent years. That's your global warming evidence. So that's kind of how you can interpret that graph, all right? Though apparently there was definitely a heat wave going on in the early 1900s as well. But more of the records, you can see that the graph is denser on the right. More of the records are being set all over the year as well, even in the colder years as well, right? Like the colder months, you can imagine we're setting these records based on the other graphs we've seen. Like even cold years or like non-summer temperatures were hotter, and even summer temperatures were hotter. We're setting records more recently for the highest high. And yeah, that kind of screams global warming at you. And that's a way to interpret this graph. Does that make enough sense? Any questions about that? It was cool, right? You can answer these questions that you're thinking of. You can see evidence. It's easier in picture form sometimes. All right, if we're good, I have one more kind of graph that I want to show you. The age-old question now is like, all right, I've got numerical things. I know how to graph them. I can do a scatter plot. I can do a line plot. How do I graph categorical things? Usually it's going to come down to this frequency count. And that is what I want to show you next. So I want to show you how to make this kind of graph. You've made it before. I'm sure you've seen them before. They're called bar charts. But it looks like this when we do it in our data science library. Okay, so it's dot bar H for a horizontal bar chart. There is just dot normal bar that is a vertical bar chart, but it's gonna it doesn't look good. Everybody does bar H for this data science library. And so this is how you can turn different categorical variables, things that are like words, strawberry, chocolate, vanilla, categories. You can turn those into different graphs this way. Okay, so that's bar charts. And I know that there's there's a shortcut for what I want to do right now, but I can't figure it out. No. Alas. I'll just do it manually. Bar charts. Okay, so let's make those. The way that you make a bar chart, here's the documentation for that. Let's go there first. It's dot bar H to make a horizontal bar chart. What you do is you say the label that you want to start counting stuff of. All right, what do you want to be on the, I guess, the y-axis? It's like, what is the categorical variable that you want to start counting frequency data out of? Okay. And so you put that, and you can also choose the kind of thing that you want to count after that, and I'll show that to you in that order, I think. It'll make more sense with an example. We just kind of say what your categorical variable is, and it kind of counts all the other columns of your table if there are multiple columns, okay? So, yeah, let's make one about ice cream. I think that would be easy. Let's make this exact graph. So I'll say, I'll make a blank table just for fun with 2 columns. And I'll say we got flavor values, and that's an array of chocolate, strawberry, and vanilla. And then I'd like to have this is like our inventory table or something. Like, let's have the number of cartons of that ice cream that we have in the back that we can give to our customers. And that will be an array of how many chocolates. Let's say we've got a lot of chocolates, 5 strawberries, and 9 vanillas. And yeah, let's call that table something. Let's call it ice cream. And then we'll print it out. So there I am. I made this table. I hope you can kind of see it. And then I can do a bar chart of it. It's a horizontal bar chart by saying ice cream, name of the table, dot bar H. And then you say what's the categorical variable that you want on the left side of the bar chart, like this. What's your categorical thing that you want to start counting things of? let's say flavor, and then I could just say it like this, and it will put like the number of cartons on the x-axis there, and like it'll graph that for me. Or you could be like explicitly saying, I want the number of cartons as the thing that's going to tell me how big the bars are. Number of cartons. Okay. So I could have skipped that second one, as you saw. Could have skipped the second argument because there is only one thing left. And what it's going to do, it's going to make this graph still. And how I want to explain it to you, the fancy word I want to say is what this graph is showing you is the distribution. That's a new word that's important to this class. The distribution of cartons of each flavor. All right, so that's my bar chart. It's showing you a distribution. How much chocolate do I have? What's the number of cartons value for chocolate? I'm turning this categorical variable into a number based on that associated numerical variable next to chocolate. Like chocolate turns into 16, strawberry turns into 5, vanilla turns into 9, kind of. That's what it's saying there. Show me the distribution of how much I have. And so you can see at a glance, like, all right, I have the least amount of strawberry, the most amount of chocolate, something like that. Does a bar chart make sense to us, and how we're asking it to make that graph and how wide it is depends on this numerical value here? But it's split into those different categories, okay? That's important, that's cool. Yeah, let's go back to, let's do some movie examples again, and I'll show you some kinds of things that you could do here. I think that's what I wanted to say. The order is going to matter as well, so let's go there. Let me include another movie-based data set. It's called, just a bunch of movies examples from this chapter of your book. It's called Top Movies 2017. So all the movies that were made up till, I think, 2017. And here's this table. All right, you've got the name, the title of the movie, the studio where that movie was made, like this top movie that we're keeping track of, how much money that movie made in terms of just normal dollars this time, over time. Adjusted gross is like adjusted for inflation to be, I guess, 2017 dollars, because that's when they took their last values, and the year that movie was made. All right, so let's deal with let's try to make a bar chart of a few different things. All right. Gosh, do I want to show that to you right now? We'll get there. It's going to be weird. I'm going to show you some things that I'm not teaching you yet, but I need it. But I've called this tabletop. Let's look at our categorical variables. We've got the title, right? The title of the movie is a categorical variable. Yes, it's just a name. The studio, as well, is another categorical variable. So here are the two categorical variables of my table. Here are the rows for each of them. Like Avatar was made by Fox Studio, Titanic was made by Paramount, all those things. Okay, and let's take that table and try to say what I want to do with it. Let's try to turn this into a bar chart. One way that we could make a bar chart for these movies based on one of these categorical variables is splitting it by studio. Would that make sense? Like how many of these top movies were made by Disney? How many of these top movies were made by Paramount? That would be a good bar chart to make, I would think. You can see like which studios are making the most popular movies that way. So that means for each studio, I need to get how many in this data set were made by Paramount, how many in this data set were made by Fox, all those things. So let's take that table with just the categorical things. Let's do like dot where the studio was Fox. And that'll give me all the different Fox movies that were the top movies of those times. And I can see how many movies Fox Studios had in this data set by saying num rows, right? Because after I pick out only the Fox ones, if I ask how many rows are left, that's how many movies were in the data set made by Fox. Does that make sense? I kind of want to do that then for every single studio. Those are my categorical variables. So I want to do the same game for like how many were Paramount, all those different things. All right. There's a quick way to do it. that I'm just going to show to you right now. I'm not going to teach it to you, but here's the secret. Let me say one thing quickly. Is that a thing I want to say? Yeah, I want to teach you an operation. Just briefly. I think I do want to do that. So I'll definitely explain this more later, but there's a dot group on tables. That's very, very helpful here. So if you say dot group, it's right here, advanced table. It's an advanced table function. Cool. What you do is you say your table name dot group, and then you give the name of a label, and it will tell you how many, like it'll separate that, it'll separate your data set by all the different values for this column, and it will count by default how many ones were a certain one, how many ones were a different one. So for all the different values, it'll group them together and count them by default. So that's what it does. And so an example is worth a million words. Let me show that to you. So I can say this. I can be like, top, give me all these guys. These are just the titles in the studios. It doesn't really matter. And then I can say dot group on the studio. What that will do is it will bring together all the Foxes, all the Paramounts, all the Universals, and it will count by default how many were each. It's a very, very powerful idea. I'll explain it more later, but this is useful for us right now. And so it looks like Disney made 29 movies, or Disney, Buena Vista Disney versus normal Disney. I don't know the difference. Maybe you do. DreamWorks made 3 of the top movies. Fox made 26. Like, these are the values that I want. I have a count for every studio. Does that kind of make sense what group did? It grouped them all together. All the Foxes, it brought them together, and it counted how many there were. There are 26 Fox movies in our data set. So it does that for all of them in just one line, and we can call this something. I'll call this the distributions for every studio, right? Studio distribution. That's that table now. And if we do a bar chart now, studio distribution dot bar H on studio, it'll get this count as the other thing. It'll turn all these names into counts this way. Isn't that cool? And you can see at a glance like how many of the top movies were made by each studio. That's a very nice looking bar chart. Any questions about how I got this? It's an interesting idea. This idea of grouping, which I'll teach us more later. But like that's a great looking graph that's useful for us. Though we could make this prettier by making the bars like close to each other that have similar numbers. So one thing you could do, it's going to go in order of this table. So if I sorted by the count, I would have a prettier like descending or ascending bar chart. So I said sort first, sort by the count column. Let's do like descending equals true. So this will sort the counts descending, so like the studios with the most movies first, all the way down, and it will turn into this graph. If I did the sorting descending first, you see like what's going on. And I really don't know the difference between Buena Vista Disney and normal Disney. Doesn't, but it looks like they were tied with Warner Brothers at the start of the bar chart there. Cool. And so it's an even prettier graph. It's going to go in the order that you give it. So if you sort it by something, it'll look nicer. That's your bar chart. Cool. Questions about that? All right. So what I'd like you to do is, let's see here. I would like you to try to do everything I just did. Try to do this kind of grouping and make something cool happen. Do the counts and things like that. Let me give you all this code updated again. So if you refresh our chapter 7 file, you'll have all the code that I just wrote. So you can see all the ways to do this. But I'd like you to try now, I'll give you a few minutes to play around, try to do stuff with the Titanic data set. All right, so try to do the following. Here's my question to you. So go and include the Titanic data set this time. I'd like you to try to find the number of survivors for each different class of passenger. And so that means like some of the passengers were first class passengers, some of them were second class, some of them were third class. I'd like you to group by that, get how many first class passengers that survived, get how many second class passengers survived, and get how many third class passengers survived, and make a bar chart of that. Does that make sense? See how you might be able to ask that question? So please give that a try. It's a harder question. I'd like you to think about it though. You can always make a brand new table by extracting stuff from the table. The quick and easy way, the non-grouping way, would be to do something like, all right, go and find all of the first class passengers on the Titanic who survived. Count them by taking numbers. Do that for second and third, and just make a table based on those numbers. That would work. There's also a way to use that group idea from the code that I just uploaded to see. There's a way to make that work as well in one line after you've done some pre-processing. So try to make a bar chart of the different number of survivors. So here's kind of what I want to see, maybe, if that helps. A bar chart that kind of looks like this. Like here's like first class, second class, third class. So it's really just going to be 1, 2, 3. And like here's the amount for first class passengers that survive, second class, third class, like something like that. But really it's just going to be 1, 2, 3. Which is interesting in itself, because isn't the passenger class values for Titanic, those are numerical, aren't they? But they're not really. 1 means first class, 2 means second class, 3 means third class. It's really numbers being used as categorical ideas. That's a huge thing. That's a difference, right? That's weird. That's important. So the P class values are really categorical values, even though it's a number. Same with survival. Same with survival. 0 if they didn't survive, 1 if they did survive. That has nothing to do with numerical math. That's just like a yes or no. They could have just said yes or no, spelled it out. Those are really categorical ideas, even though they're represented in the data set as numbers. We have to differentiate. So it makes sense to put the passenger class in a bar chart, because it really is just categorical. Well, yeah, I'll give you a couple more minutes to try that, and I'll do it too. This is not going to work in time. All right, that was my timer. Any questions about this as we tried it? You kind of get a graph that kind of looks like that drawing or chart? Let's see. So let me include the Titanic data set, and we'll go from there. So there's my Titanic data set. I saved it as Titanic, and I only care about the survivors. So I want to get it where it was survived being 1 and not 0. Only the ones, right? Those are all the survivors. I want to pick out only the survivors on the Titanic. So that's going to be a .where condition, right? Titanic .where the survived values are set to 1s. So there's all the 1s. Oh, sorry, I didn't spell survived properly. There they are. All the 1s. Those are all the survivors on the Titanic. It's a brand new table. I can call it Titanic survivors. Something like that. All right. So, yeah, I think that's what I wanted to say for that one. Dun, dun, dun. So now I have all the survivors, and if I want this kind of idea, it's going to be based on the passenger class, the P class. Were they in first class, second class, or third? And you could make your own table if you wanted to, like make a brand new table with just the data you cared about if you forgot how to do the dot group, because I did show that very fast. I'll teach it to you in detail later. But you can get all the first class survivors by saying, all right, here's all the survivors, Titanic survivors, dot where the P class values were 1. There's all the first class survivors. Does that make sense? Here's all the first class survivors, because I took the survivors table and I filtered it out where the P class was exactly 1. So if I wanted to know how many first class survivors were there, I can say num rows now. It's like, give me that table, the number of rows. There were 136 first class survivors. I can do the same for second and third. I can turn that into a table if I wanted to. I can call that like first class survivor count. Something like that. If you wanted to, that would work. That would totally work. But you could also, another way to do it is take the Titanic survivors, and then you could group it by P class. And then it will just by default separate them into the passenger classes and count how many were in each row. It was already the survivors. So it got the 136 first class survivors, 87 second class survivors, and 119 third class survivors, which is surprisingly close to how I randomly drew the graph. And then you could do a bar chart. And then you could be like, dot bar H. What's the categorical thing? It's P class. Even though it's a number, it's secretly categorical. All right. So based on the passenger class, the first class passengers that survived, there were that many. That was the most. Then second class passengers, not as many. And then third class passengers, close to the same amount of first class passengers that survived there. Okay. Any questions about that? Because you could also do other things. You could be like, there's a bunch of things we could do now. It's very cool. We could ask, so like this was first class, there were that many first class survivors, but maybe there were a bunch of first class people who didn't survive. Like maybe they're just mostly first class passengers on board, and that's just like randomly, or that's the reason why there were so many first class survivors, because there were just more in total to choose from. We can ask that same question by going back to the original Titanic table and being like, hey, group by even the survived and the non-survived, tell me the total amounts. Group by P class now. See the difference? What the difference is going to be now, this is like the total first class passengers on board the Titanic. See that? Survived and didn't survive. Second class, third class. There are many more third class passengers, it seems. And you can do the same thing with the survivors. We already did that here with the P class there. And you can kind of do a ratio now, like how many first class survivors were there out of all the first class passengers total. You can do those things, and you can ask for them, right? These columns, couldn't you? Like, give me the survivors for each class. Give me how many were total on each class, divide this by that. If I did that division, I get the ratio of each passenger class and how often, like, what was the proportion of them that survived. Isn't that cool? So I can take the ones that were here, and then I could be like column count, right? Because it's called count. It's making that default column. And there's my 136, 87, 119. I can divide that by the 216, 184, 491, right? By the totals. Give me the column count there. You see that? And then I've got proportions of how often, like what was the likelihood that a first-class passenger survived, like what was the proportion, the true proportion, is like 63% of the first-class passenger survived, about 50% of the second-class passenger survived, and almost 25% of the third-class passengers survived. So you get a better picture of what was going on with proportions. You see how I generated those proportions? That's pretty cool. I like that. So we can turn that into now a table and make a bar chart out of it all. It's like you can always start with a blank table and you'd be like, all right, let's add some columns to a blank table. First one can be the P class. What was the passenger class? That's an array of just 1, 2, 3, right? 1, 2, 3. Or you can say first, second, third. You could spell it out if you wanted to now. And then I want like the proportion of each of those classes that survived. Proportion. And I'll say something like this. I'll put exactly this array, which is calculated in this way. I'll just put it right there. Why not? And then I'll say, all right, there's my table. I've turned it into a table. I'll just like put these proportions next to the P classes now by making a blank table. Then I can say dot bar H on the P class. And now the bar chart that I get is the proportion of first class and second class and third class passengers that survived the Titanic. And you can compare that to the counts of the ones that survived, even though a decent number of third-class passengers survived relative to the first-class passengers in second class. It was far fewer than the total for third-class passengers. All right? So that's the proportions of the people that survived of their different ticket classes. So the third-class passengers, on average, they did not do too well, sadly. Any questions on how I made that? All right, so the last things I want to talk about, we'll just go kind of quickly, but a few more things to say. Before I get there, I do want to say, though, when you're making charts like this, you can trick people very easily. I do not want you to trick people. Use your powers for good, please. Here are some thoughts, all right? Here is like a graph from a news show. And they're like, all right, if the tax cuts expire, here's how much you're going to have to pay in taxes. Right now it's 35%. Sorry, it's very blurry. But eventually it might be 39.6%. Do you see what they did? This is not at all relative. 39 and 35 are really close to each other. This looks like, if that was 39, this looks like 10 or something. They're scaring people. They're cutting off the graph. They're zooming in on a part of the graph. That's disgusting. When in reality, this is the graph, right? That's the real graph, 35 versus 39.6. They're really close, more or less. So you can scare people by doing that and making the graphs look wonky and weird, even though it's still a graph. So don't do that. Use your powers for good, please. All right. The last topics for the day that I want to talk about, I want to ease us into this idea of distributions. We won't complete these slides today, but we'll get a little bit of the way in. So it looks like this. This is what a distribution looks like. You got like values for ranges and things. You may have heard like the idea of a normal distribution, like a bell curve. Maybe you've heard that word before in like a statistics class if you took one. And we will get into like these nice, pretty curve distributions eventually, but we'll start with these. How many values are within a range? That's what it means. How are values distributed? That's the kind of question we want to ask. How are values distributed within a range? Okay, so we've got a bunch of different terms to talk about these ideas with. Some of them I've already said. Let's just hit them hard right now. So individuals, those are like your rows of your table. It's like the people who you've recorded attributes for, the people on the Titanic, the different ice cream cone flavors, the different movies. Those are your individuals, whatever the rows of your table are, the things that you're recording attributes of, okay? And then variables, are your columns. Those are your attributes: the color of your ice cream, the price of your ice cream cone, whether or not the Titanic passenger survived. Those are called variables in another way. And we know that those could be numerical or categorical. What was the name of the passenger? How old were they? That's a categorical and a numerical, right? You've got, all those different variables have different values. Like you got some 20-year-olds, 22-year-olds, got some 2-year-olds that were on the Titanic, right? Different values, and each individual had just one value. It's not possible for our data sets, right, to have like, all right, the passenger class for this passenger was 1 and 2. No, you just get 1, right? So each individual has exactly one value for each variable involved, for every column. And all those values, if they're numerical at least, they have a distribution. And even if they're categorical, you can count their distribution as well. So every variable has a distribution, and it's like for every different value that it takes on, what's the frequency of that? How many chocolate ice cream cones do I have? How many vanilla ice cream cones do I have? That's a distribution, right? What's one versus the other? What are their counts? How many people are age 22 on the Titanic? How many people are age 32 on the Titanic? That's a distribution. Like, show me the difference. That's what that means, all right? So in general, the idea of a distribution is you're telling me who's in what. You're keeping counts, all right? So when you have a distribution, it does look like this. Like, what are the values in those ranges? And everybody gets one category, okay? Which means that if you take percentages, they're all going to add up to 100%. Okay, so here's an example of a distribution. So like they surveyed some people in the U.S. and they asked them questions about how often do they go online. Pretty much everybody does, of course, right? Some U.S. adults they got to choose among these values. They were almost constantly online all day. Several times a day they got online. Once a day they got on their phone or their computer or whatever. And then some people a lot less often, probably old people. So everybody was in one category. You can't choose like, I am online almost constantly and several times a day. You pick one. That's the distributions. You're in one or the other, all right? Every individual in your data set, in your survey, is in one category. So if you take percentages, they add up to 100, okay? So that's what a distribution means. Some things that have values are not distributions, right? So here's an example that's not a distribution. They took some people took a survey and they asked people questions that they could pick more than one answer to. They asked like, all right, during COVID times, what's a reason why it would be hard to quarantine yourself for at least two weeks? And they let people pick more than one answer. So like some of them, like 40% of people said they have too many other obligations. Almost 40% said they were unable to miss work. 23% of the respondents said that they were concerned about being away from people. They didn't like that. And we've already added up to more than 100 for those first 3 categories. Does that make sense? That's not a distribution because of that. You can only have one place that you're in a real distribution. So this adds up to way more than 100, so it's not a distribution. If they let them just pick one option only, then it would have been one, but it's not. All right. This is a distribution. Everybody got to pick one only spot to go in. They picked a bin for themselves. And then this is not. Okay. And that word, that we're almost there, that word gives us kind of where we're going next. So the idea of binning is putting people in a spot. All right. Putting people in a spot that is important. Let's see. How do I want to do this? So I want to go to there maybe. So, okay. The idea of binning is sometimes you have a distribution and nobody takes on the same value, right? So like you got all these movies. No other movie made exactly, what is this? No other movie made exactly $906 million, $723,000, and $418, right? No movie made exactly that much. There's just one in the data set that made that. No other movie made exactly $760 million-ish, right? They're all in one separate category. But you could take some of the ones that were in ranges and count them. You can put them into bins. Like how many movies made between $750 million and $1 billion? How many movies made between $500 million and $750 million? You can count those, and you could bin them. You can shove them into little bins in a range and see what's where. That's the process of binning, and that gives us a distribution for variables, right? For numerical variables. And so yeah, binning is like you're counting the number of things within a range and you're putting them into bins. So this is a little bit technical. The way that bins work is they're within a range, right? They're within a range, and the lower bound is inclusive and the upper bound is exclusive, all right? So bins are defined like this. They're defined by their lower bounds because you can there's always like a range of what they're in, and the upper bound is the lower bound of the next bin, all right? So let's say I've got some numbers, right? I've got some numbers and I like to see what values lie in which ranges, because like I've got a bunch of numbers and they never repeat, right? Usually they're not going to repeat, but I know that they're all within ranges. So let's say that I want to bin these numbers by 5s, all right? So I'm going to like draw lines between like 160 and 165. Like that's going to be a bin between 160 and 165. All the values between 165 and 170, that will go in a bin. 170, 175, that'll be another bin. So like I'm just counting things in ranges because like I'm never going to have like 166. I'll have like 166 and maybe like 166.25. They'll never be the same, but they'll be within a range. And I can count them that way. So that's useful. That's useful for me. But the way that these bins work is going to be a little technical. The way that we're going to put values here is this is the 160 to 165 bin. But the values that you put in here are all the values that are between 160 exactly up to 164.99999. That's the way these bins will work. The left side is inclusive. The right side is exclusive. If there was 165 in this data set, you count it in this bin. Does that make sense? The right half of that bin goes somewhere else. Okay? That's how that works. So let's bin these numbers. So 188, it's between 185 and 190. And it's not strictly equal to 190 because 190 would go over here. But 188 is between 185 and 190, inclusive and exclusive. So I'll just like add a little line there to mark that I've seen that one. Does that kind of make sense? I'm putting it in a bin, and you can see the relative amounts in each range that way. So 170, which bin does that go in? It's not the 165 to 170 because that's like inclusive and exclusive. It's in the 170 to 175 bin. Does that make sense? It's always going to be like that. So 170 is going here, and I'll draw a little line to mark that we counted that one. And then 189, where does that go? It's this one again, right? Between 185 and 190. 163 goes in this one, right? 160 to 165. 183 goes here, right? 171 goes here. 185, it does not go in this one because that's the 180 inclusive to 185 exclusive. It goes in the next bin, right? That one goes here in the 185 to 190 because it's always inclusive on the left, exclusive on the right. That one goes there, and then we got 168 and 173. 168 goes here, 173 goes here. Does that process make sense? Any questions about that? You never had the same value, but because we split it up into ranges, you can see that some of these pieces, some of these ranges have more values, and that's important. That's useful knowledge for us. All right, we've binned them, even though they never take on the same exact value. You see ones in certain ranges. Okay. So that's the idea. That's the idea. Yeah, that's what binning is about. Gosh, do I want to show that to you at all right now? We'll get there in a second. I really do want to do. There's a dot bin operation that I want to show to you, but before we get there, let me show you something and kind of where we're going in the next lecture once we get there. So okay, not too much left today. When you do bins, as long as your ranges are of equal size, you don't have the problem that I'm about to tell us about. But if your ranges are different sizes, then you do have to worry about this. So you do have to be a little careful when you're drawing pictures of your bins. You're making distributions that kind of look like this. This is eventually where we're going to go and build graphs that look like that. But like this is what we did. You do have to be a little bit careful. And here is like the way that you draw pictures really matters to the human eye. Okay, so here is a picture from an Apple conference. They were releasing a new iPad, and they're like, all right, this iPad, the one that they're announcing, had a 70% bigger battery. And they made this picture to show that. Do you see how this is misleading, this picture? Because this is for sure, this is not a 70% bigger battery, is it? What they did is they took this picture and they enlarged it by 1.7 times, probably. That's what happened. It's 1.7 times wider. But do you see how that also made it 1.7 times as tall as it was? We as humans, we see relative size in terms of areas, not in terms of the length of one of the axes. How many of these batteries can you fit into here? Probably like 4-ish of them, right? You see that? So it makes us think as humans that this new battery must be like 4 times as good. But it's only 1.7 times. It's only 70% better. Do you see the misleadingness there? That's a bit of a problem. So the way that we draw our bins and the way that we size them better deal with area rather than width. All right, so this is a question of area versus width when we're making graphs. Width or height taken singularly. Width. Let me draw that in a way that is legible. And we choose area. Area is the way that, as humans, we imagine things should be. So if it's like 1.7 times, you should make the area like 1.7 times as big. Like something like that is what it should have been. And then you can kind of clearly see it's not the biggest difference in the world. But it is a bit bigger, right? 1.7 times the area for that battery. So that's probably what it should have been. And you can see the relative difference. Does that make a little bit of sense? That's odd, but it's useful. All right, so yeah, that screams that when we're drawing our graphs that's supposed to represent proportions of things, we should use areas. Areas should be proportional to the values that they represent, all right? So that means if we're drawing pictures and we're like 20% of the population is a triangle, then you can't be like, the correct way to represent then 40% of the population is draw 2 triangles, right? You can't do this. You can't be like, all right, 40% of the population, if this is a 20% triangle, a 40% triangle can't be 2 times the width. Does that make sense? It can't be 2 times the width because that makes us think weird things. This is 2 times the width. But what did that do? How many of these triangles are in this? Now there's 4 of them. Do you see that? When you double something, because you doubled the width and the height, you quadrupled its area. We heard that rule before? We quadrupled the area. Scaling a shape by a factor of 2 scales the area by a factor of 4. You can see like the little Triforce in there if you know Zelda. But like this should have been the 40%. This is not representing 40%. It's not double this. It's double the area, not double one of the axes, and stretch the other one too. Okay? That's what I mean by that. So you have to be, don't mislead people. It's this idea all over again. You better be using areas when you're showing relative differences. Okay? Otherwise you'll mislead people, people will get confused. Okay? So let's see. Yeah, let me show you how to bin stuff. There's just real quick. Won't take that long. And then it'll be time to work on stuff. Where were we? So I'll show you distributions, bins, and histograms. That's where we're going. This is a very fancy kind of graph that we're going to learn how to make based on these ideas of bins. So let's go back to our top movies data set. Let's make them pretty. Gross is hard to read. Gross adjusted is hard to read. Let's format them with the number formatter. So set the format of a bunch of columns at once with an array of columns 0, 1, 2, and 3. That's the 2 gross columns, columns 2 and columns 3. And we'll set them with number formatter. Boop. And so now you got some line. You can see that. Okay, that's 906 million. That's easier. So there's that. And let's turn these into, this is like a lot of digits. Let's turn them into how many millions of dollars. So we'll divide them by $1 million, each of these values. So I'll turn this into, like, take the top. Let's pick out the adjusted gross. All right. And that's top dot column number what? 0, 1, 2, 3. It's easier to type. So column 3 is the adjusted gross values. Let's divide them all by 1,000,000. So you could spell out 1,000,000, or you could do 1e6. E means times 10 to the. So 1 times 10 to the 6, that's $1 million. This is all now adjusted into millions of dollars, so 906 point something million dollars for each of those. And let's add that back into the table. All right. But maybe we can round it too, like np.round all these values to the nearest 2 decimal places. So that's cleaner looking maybe. And let's put that back in the table. Be like, all right, select out the name of the movie, or like the 0th column, right? Select the 0th column, so I got just the names of the movies. I'm going to shove this into another column. I just got the names of the movies now, but I want to add that column back in with a column that is what I just put. I'll say adjusted gross, and I'll put the values that I just found right there into them, and I've just made that. All right, so a bunch of millions of dollars. I'll call this millions. So that's my new table. And what I'd like to do is bin them, all right? It's like, what is the, where should the bins start and end? Like, I want to kind of do this. So where should it, like, what's the minimum value of adjusted gross? What's the maximum value? Where can I start and end my bins? That's the question I want to ask right now, okay? So I can find that in this way. I'll be like, all right, give me millions dot column, I called it adjusted gross. Give me that column. I'll call that something. Like I got all the values in that place. Give me that column. We'll call it adjusted gross. And then I can ask for the minimum of that. The min of all the values in that array that I got back. There's a min function in Python. There's also a max function. If you want to print out a couple things at once, you can put a comma between them. So like I want to print out the min of adjusted gross and also, comma, the max of adjusted gross. And that's the range of values. So some of them made out almost $1.8 billion. Crazy. So that's where my bins can go. That's where I can range them. But also min and max kind of tell you a little bit about the distribution of these values, right? So min and max, we can see that you got some movies, like the lowest end of the movies made this much, the highest end of the movies made this much. But min and max don't tell you the full story, do they? They don't tell you, like, were most of the movies not making a lot of money, and then there were a few that made a ton? Or maybe not many movies made a little bit of money, but a lot of them made a lot of money? Or like, it looked like that? What was the distribution of those values? Min and max don't tell us, they just tell us the ends, don't they? We don't know, like, we don't know what was going on between those ends. Like, did it look like this? Did it look like this? Did it look like this? Those are still between the same min and max values, but they're completely different graphs. They're completely different distributions, aren't they? So if we bin them, we can see a better picture. So min and max alone don't tell us much about the distribution. But at least they tell us where our bins can start and end. But they'll help us bin things. So yeah, there's a bin operation on a table. You can be like, millions is our table. This is all I wanted to say. There's a dot bin, which is very nice. And you can bin by what? I want to bin by the adjusted gross value. So I give the name of that column. And it's just called dot bin. And it makes, by default, 10 equal-sized bins. And I want to show them all and how this works. So this automatically makes 10 bins for us, even though it's giving me 11 things. Automatically makes 10 bins. I want to show you how to read this and understand it. Okay, so let's see here. Dun, dun, dun. So okay, what it's done, the way that you read this dot bin thing, it's binning these values. It's come up with the range that's like an even amount, like the different values. It's showing me where the bins are and what's going on with them. The very first bin starts at the way that this works. So it made the very first bin starting here, 3.22.26, and it's ending at this value. The next column, or sorry, the next row in the same column is telling me the ending value of that bin is it's making 10 equal distant bins. So this first bin is between 322.26 to 465.813, not including that one though. So that's the first bin. It's between here and here, and it's telling me how many things are in that bin. 112 movies. Between here and here. Do you see how you're using the next one to interpret the previous one? That's how you read what was in that bin. Then the next bin is between 465-ish to 609-ish. That's the next bin. And the number of movies within that range are 52 of them. All the way down here, from here to here, there was one movie. And then finally, for the last bin, between 1.6 billion to 1.7-ish billion, there was one thing. And then this last number is always 0. It makes no sense. It's not part of any bins. Okay? So I hope that kind of makes sense how you can read that. But you can turn these bins, like this is just the default bins, you can turn them into something normal. You can bin by a certain range of values. All right? And these are the range. This column is the range of values. We can say something instead of that and be like, all right, it's like 320-ish to 1800-ish. Let's go from there to there. It's like np.arange. You can make your own bins in this way. 1801, go by like hundreds. Let's say that I want these to be my bins. You can tell .bin to bin with them. And the way that these bins would work is it would always do them in line. The first two mean the first bin is between 300 and 400. The next bin would be between 400 and 500. The next bin would be between 500 and 600. That's how you tell it which bins you want. It's just the next two elements of your array. And then the very last bin is between 1700 and 1800. See that? And that's perfect. That would contain the last thing, the maximum. All right? So you can say, like, these are the bins I want you to use. You give an array of the different starting and stopping points for each of the bins. It's going to go in that order. It's going to take the two things next to each other. So I can say instead millions.bin on the adjusted gross values, and bins equals these ones I want you to use, please. And so now what it's done, I can say .show to show everything, is it's binned all these values. How many movies made between 300 million and 400 million? 81. How many movies made between 400 million and 500 million? 52. So I gave these exact bins that I made with arange to .bin, and it shows me the distribution that way numerically. Are there any questions about that? Because we eventually want to turn this into like an actual graph. You kind of see how this .bin is working. It's a little weird. I don't actually know if this is on any of the pages, but we need this first. .bin. Yeah, it's not on that page. Okay, it's on this other one. So you can read more about it there. It's grouping values into intervals known as bins. But yeah, that's where I wanted to start. All right, so that's how you can make a bin by default, it gives you 10, or you can say, I want you to use these exact bins by giving an array with starting and stopping values for each bin, between there and there, there and there, there and there. Okay, that's what I want. And then I kind of want to turn this into a graph, and that's called a histogram. That's the last slide I want to do today. I want to turn it into that. I want this graph, please. How many are within this range? How many are within this range? It'll give you a bar for the range and the count, right? Which is really a proportion. So let me show that to you, and that will be the last thing I believe we'll do today. Yeah. Where is my bar? There it is. That's always hard to find. Okay, so I'll make these histograms and show that to you. So the idea of a histogram is it's showing you this binning process. It's displaying a distribution of a numerical variable. It's like your adjusted gross values for your movies. And every bar is the relative proportion in area, right? The relative size in terms of area, given everything we just said, for each bin. So you can see like between 300 and 400 million, that was the most amount of movies. It's the area principle, right? So every bar corresponds to one bin. It uses that area principle that we just talked about, where the area of each bar, if you add it up, you see how much blue is there, is the percent of the individuals in your data set that were in that particular bin, all right? It's not really going to matter when your bins are of equal lengths, but the second you have unequal bin widths, that really matters, all right? And so the way that you do this is honestly, you just say instead of .bin, you say .hist. This is called a histogram graph, right? So .hist, it works like this. You give it a column, you optionally give it which bins you want it to use, and it will plot a histogram of the values for that column. So it defaults to the 10 if you don't say which bins to use, but if you say an array of bins, it will use exactly what It's what I've been trying to tell you. Like, you give an array of things. If you got 3 things in your array, that means you got 2 bins, between 1 to 3 and between 3 to 4. Kind of see the range there. All right, that's how that works. And again, you could use instead of the name of the column, you could use the index. That would totally work. But it also takes a unit argument, and I'll show that to you too. But that's the last thing. So, okay, instead of .bin, you can see like the relative amounts. We could also do .hist with those same things. .hist, please, give me a histogram. Oh, oops. I don't say .show anymore. Sorry, .hist just makes the graph. So there it is. And you could also say what the unit was. So adjusted gross, what was the unit of that? You can say unit equals whatever it was, and it was in millions of dollars. So I'll say $1 million. That's the unit value. And so then it puts it between quotes here. Adjusted gross in millions of dollars. And then now you can kind of read what was going on here. All right. So we gave it the bins. We wanted the same bins. So between 300 and 400, there were 81 movies. Proportionally, that was a lot compared to the other numbers here. And you can see that on the graph now. So this histogram it's showing you, it made a bar between 300 and 400, and it put the relative proportion in terms of area, right, for how many were between that amount and 300 and 400 million dollars that made that much on the graph, right? Between 400 and 500 million, the movie's making that much. Relatively, proportionately, there are that many. Does that kind of make sense? So you can see it at a glance what the distribution of these values looks like. It looks like there were very few movies making a whole lot of money. Most of them made a little bit, which is still a lot when you have over $300 million. But relatively, they're in the lower range of gross revenue. Okay, so that's what a histogram is. I'll explain it more in detail next time, but are there any questions about any of those ideas? So we're taking a numerical variable and seeing what values are within a bunch of different ranges. How many are within this range? How many are within this range? And showing the proportions of those things. Because they'll never be exact, but like you can totally put things within bins. Because you know a few things are going to go in this bin, a few things are going to go in that bin. Even if the amount of money that those movies made is never exactly the same. They're always at least $1 away, right? But this one is going to put them in the same spot for the bin, at least for the graph. And then just as we did before with the .bin, if you don't give which bins to use, it will give you the default of 10. It'll break it up into 10, and usually that's good to start, but sometimes you want to split it up further. So by default, it makes the same default 10 bins for us. And so you see it's like something weird, some weird values. You can go back up here to see what it was. Between 322.26 to 465.813, there are 112 movies in that range. And that is proportionately this many. This y-axis I don't want to explain today. Percent per $1 million is what it's saying. This was like almost 0.4% of movies per $1 million. It's a weird ratio. Doesn't make a lot of sense right now, but it has to do with that area idea. All right? I'll get to that next time, though. So are there any questions about the idea of binning, where you say, like, what your ranges are? Like, between this bin and this bin, it'll start counting. There are these many values for adjusted gross. Between this bin, 400 and 500, there are this many values. You can kind of read that, because that's going to be turned into your histogram. That's what the graph will show. And it turns into that, and it's pretty. It shows you the relative distribution of all the values for that numerical attribute that they took on. And that is, I think, where I want to stop if we're happy. So that's what a histogram is all about. That's like the last and fanciest way to make a graph for this chapter, kind of. We started with just like, all right, we got a bunch of x and y values, scatter plot it, line plot it. We got some categorical stuff, count some things somehow from it, make a bar chart. And then histogram is the fanciest, where we needed all these ideas of area and things. I'll explain it more later. But you're going to put values within different ranges within bins and start counting how many are within each bin. Relatively, how many movies are between $300 and $400 million? How many made between $400 and $500 million? How many made between $500 and $600 million? And you can see the distribution. You see the range. Not as many movies were making a lot of money. most of them were making a smaller amount of money, like they were made by like they were niche movies that didn't really like make it big, but they still made a decent amount of money. Very few movies made a lot. And that's what the distribution is showing us, and a histogram shows that to us. All right. Yeah, so I think that's all that I wanted to say for the day. I'll stop us there. I'll give you everything that we did. And yeah, make sure, let me know if you didn't get to attendance, but I want to stop here to be continued. And I think that is all I wanted to say for the day. Yeah, that's where I wanted to stop. And I'm good to stop the recording too.